In this video, we are going to learn about propensity score. Propensity score, a method of data reduction. The biggest advantage of randomized clinical trial is that proper randomization provides a balanced distribution of both observed and unobserved factors between study arms, which minimize confounding. Observational studies often suffer because such balance no longer exists. Multivariable regression can provide adjusted estimate for the main exposure variable by including confounders simultaneously in a model. However, when more than the allowable number of covariates need to be adjusted, we may further need to consider plausible data reduction. Propensity score adjustment is a method to control for potential confounders for the association between a pre-specified exposure variable and outcome variable, which provides a quasi-RCT setting for analysis, often from observational studies. The propensity score analysis has become popular because it creates a single score estimate of the probability that the person has or has not had exposure of interest, which is used to control for many potential confounders at once without the loss of analytical power. Is considered as the most aggressive adjustment for measured confounders. Okay, so in this lecture, we are going to learn how to collapse these many covariates into a propensity score, and so that we can analyze effect of SLE to coronary calcification without a bias. This is a number of papers using propensity score in PubMed by calendar year. As you see, use of propensity score has been increased dramatically last decade. So it is perhaps one of the most popular topics in statistics for people especially doing pharmacoepidemiology, an observational study to evaluate effect of drugs. After we review concept using this paper, we go back to our data set in analyzing effect of SLE on coronary calcification. Okay. So this is a study published in JAMA assessing effect of aspirin on all-cause mortality among patients being evaluated for known or suspected coronary artery disease. This is a prospective cohort study conducted at the Cleveland Clinic and using data from 1990 to 1998. Mean follow-up time is 3.1 years and 6,174 patients undergoing stress echocardiography for evaluation of known or suspected coronary disease were included. So let's look at the result of this study. And this is a Cox regression unadjusted for anything. So simply, they included aspirin use in the model and computed hazard ratio. And based on this, and it say use of aspirin increased risk of death or hazard of death by 8%. And although it was not statistically significant. So even though it was not statistically significant, but do you believe aspirin did not work to prolong people's life or even potentially be harmful? Before you make judgment, let's look at who were included in this study. There are 2,300 patients who used aspirin at the baseline, and there are 3,800 patients and who didn't use aspirin at the baseline. And if you look at the potential confounder, these are the factors associating to the death. So if you see imbalance, and these factors may confound study results. So let's look. In aspirin group, mean age is 62, whereas mean age is 56 in non-aspirin group, and 77% men in aspirin, 56% of men in non-aspirin. 53% of patients in aspirin group had hypertension, whereas 41% of patients in non-aspirin group has hypertension. And if you look at prior coronary artery disease, 70% of aspirin patients had history of CAD, and only 20% of non-aspirin patients had a history of CAD. And 30% aspirin patient has prior bypass surgery, and only 6% in non-aspirin had prior bypass surgery, and so on. So clearly, people who are using had the reason to use aspirin because they are sicker and they have higher risk for death with cardiovascular disease. So if you know this and take a look at this hazard ratio, what do you think? And do you think aspirin still did not work? Without aspirin, and the people who were in aspirin group, and they would have had much higher mortality rate, right? So if they end up having a mortality rate very similar, that's probably indicating aspirin was effective. I just made an inference of effect of aspirin using my head. And how did I make inference? And when I made an inference on effect of aspirin, I took into consideration the difference in terms of disease severity between these groups. So I gave extra credit for aspirin group because they started being sicker. So if you can do similar analysis by using computer, that is statistical adjustment. So if you conduct Cox regression by including age and sex in the model, okay, and what it does is it discounts death due to excess age and excess rate of male. If you believe older age is high risk and being man has a higher risk than being female for cardiovascular death. So adjusting for age and sex, okay, and we discounted excess rate of older age and male in aspirin. So after you do that, adjusted hazard ratio is 0.75. Okay? And if you further included history of CAD, so you are now discounting 70% versus 20% difference in CAD. So 50% higher difference, higher rate of CAD. So you're discounting that. Then hazard ratio becomes 0.57. And if you include everything in Cox regression, and adjusted hazard ratio becomes 0.67. So the bias which occur when the comparison groups has different severity of disease, and therefore when you directly compare two groups in terms of outcome, and you may mask effect of your exposure of interest. So in this case, aspirin group has a higher severity. So if you ignore that fact and directly compare aspirin to non-aspirin group, and you may not be able to detect the effect of aspirin. So this is called a bias by confounding, and especially in pharmacoepidemiology, when the confounding occur for the effect of drug in observational study, we call this a bias by indication, because people who use drug, they have indication to use drug. Therefore, and drug group is usually sicker than the non-drug group. So if you don't consider this confounding, and you will mask effect of drug. Typical method to control for confounding is stratified analysis. So you divide data set to, for example, patient with history of a cat, and then everybody have a history of a cat, therefore it cannot confound your study result. Or matching, when you look a patient who use aspirin and then you match a patient who does not use aspirin and whose age is the same, gender is the same as the person who use aspirin, and you match, put them in a pair. And after you do that for all aspirin users, distribution for each baseline variable between aspirin would be the same between aspirin users and non-users. Although when you have observational study, there are so many confounding factors, so it is almost impossible to use stratification or matching to adjust for all confounding factors simultaneously. Therefore, the number one choice for adjustment for confounding is regression analysis. So we use statistical tool to adjust for confounding. So, although when sample size is limited, we often cannot include all possible confounding factors in a regression model. Or when you build the regression model, and if you have improper model, such as the model doesn't include interaction or nonlinear effect, and it can lead to a biased result. And therefore, in order to more effectively control for confounding, propensity score method was developed. There are 4 methods using propensity score dealing with confounding. First, propensity score matching. Second, propensity score stratified analysis. Third, propensity score adjustment. 4, inverse propensity score weighting. Before we talk about each of the 4 methods, let's talk about propensity score. So what is a propensity score? And propensity score is a balancing score, which is a predicted probability of a binary logistic regression where dependent variable is use of drug, which is a main exposure variable. Okay? So here, if you build logistic regression and outcome is aspirin use, yes and no, and independent variables are the all possible confounders. Okay? And predicted probability of that logistic regression is propensity score. And this is 2 mathematical definition. So let's look at more ordinary example. Okay? So look at this man. A man whose age is 80 years old with a history of CAD, with hypertension, diabetes, and how likely do you think this person uses aspirin? Okay? And you think it's 80%? That 80% is a propensity score. Let's look at another example. A woman whose age is 60 years old with no history of CAD, no hypertension, no diabetes. How likely do you think this person uses aspirin? 30%? So that is a propensity score. Okay. So let's think of a person who is sitting next to you, and let's predict how likely that person is using aspirin. So everybody have a different propensity score, different likelihood of using aspirin. So that is a propensity score. So the person who is sicker and they have higher likelihood of using aspirin. So let's talk about propensity score matching. So this table 3 is a baseline table they examined for same sets of covariate after they selected subsets of patients and who are matched by propensity score. And the first thing we need to check is sample size. So there are about half of aspirin users included in the matched cohort. So 3,151 patients. And originally they had 2,310 patients. Okay. So about 1,000 patients were not included in a matched cohort. And then for each patient who used aspirin, and they matched patient who didn't use aspirin, but whose propensity score is exactly same as the person you picked using aspirin. So let's look at those 2 people. Those 2 people are having the same likelihood of using aspirin. So you matched 2 patients who look exactly similar in terms of age, sex, a history of diabetes, hypertension, and history of CAD, and smoking, and so on. So by looking at them, and you can't really tell which one uses aspirin and which one doesn't. One person is aspirin user and one person is non-aspirin user. Okay? So when you do that for every single aspirin users, you end up having the same number of patients with non-aspirin users. Okay, so let's check. difference in terms of these baseline factors. Now you see these two groups are pretty much balanced. You may realize table is as balanced as you are looking at data from randomized clinical trial. So, propensity score matching method is so-called quasi-randomized experiment. So you use observational study, but by choosing a subset of patients in whose baseline characteristics are similar, you created the study as you conducted randomized clinical trial. So after you have balanced groups and you have data similar to RCT, therefore confounding is not the issue anymore. Therefore, adjustment for confounder by regression is not as important. So this is a comparison of a mortality between aspirin group and non-aspirin group using matched cohort. So you have smaller n here. And now hazard ratio become 0.53 and effect is significant. So you can say there was 47% risk reduction of death by using aspirin compared to not using aspirin. So matching is beautiful. Although one thing I want you to keep in mind, difference in sample size. So original analysis you had nearly 6,000 patients, and new analysis you end up having about 2,700 patients. So what is happening is, so this is the schematics of what is happening. Okay, so y-axis is the likelihood of having outcome, likelihood of having death. Okay, and then x-axis is a propensity score. So the larger propensity score indicates sicker the patient. So aspirin users indicated by A, letter A, and there are more sicker patients here. And then these patients are so sick, therefore you couldn't find the people without aspirin and who are as sick as these patients. Because if you're a doctor and you will place every sick patient with aspirin, right? So you can't find sick patient not using aspirin. And a similar thing. And non-aspirin users are have a good prognosis. And therefore, you can't really find aspirin users who are as healthy as they are and still using aspirin for cardiovascular reason. So therefore, these two groups of patients who are at extreme side are excluded from the analysis. Therefore, the difference you're seeing may be smaller than the difference you would obtain if you have data from entire cohort. Second, propensity score stratified analysis. Okay. So propensity score stratified analysis, instead of matching one aspirin users to non-aspirin users, what you do is you classify patient into, this example, 5 groups based on propensity score. So if the patient probability of using aspirin propensity score is less than 20%, you place them in group 1. Okay, some of them are using aspirin, some of them are not using aspirin. And the patient whose propensity score is 20 to 40%, you put in group 2. Similarly, 40 to 60% you put in group 3. 60 to 80% you put them in group 4. And 80 to 100% you put them in group 5. So within each group, you compare mortality. So y-axis is proportion of patients who actually died. So within each group, you compute hazard ratio. So you may perform Cox regression to get this hazard ratio. Okay, and presenting 5 different hazard ratios are confusing. Therefore, in the final analysis, you pull all 5 hazard ratio and present pulled hazard ratio is 0.62. And there is 38% risk reduction by using aspirin. Next method is propensity score adjustment. In propensity score adjustment, and typically you analyze data. For example, if you are assessing effect of aspirin status on mortality, okay, and you use Cox regression, okay, and include aspirin status and adjusting for potential confounders. And instead, in propensity score adjustment, you replace these potential confounders with propensity score. So this way you replace many potential confounding variables into one factor. Okay? And let's say number of variables you can include in the model is depend on sample size, right? So here, if we have 100 patients who died, and you can include up to 10 variables, and you have only 2 variables in the model, then you can actually include more variables. So it is recommended, even after you include propensity score in the model, it is better to include factors which are highly influential on outcome variable. So in this case, age and sex, and maybe CAD and other risk factor for death, and you can include as long as it is within the allowable number of variables. And in propensity score adjustment, and instead of using predicted probability here, okay, this means predicted, and it fits better or may improve power if you transform predicted probability in the logic form, which is log of predicted probability over 1 minus predicted probability. So you can easily compute this in SPSS. And this is what they did in their paper. So after they selected subgroup of matched cohort, okay, and they did not really have to do adjustment, although they did conducted analysis including propensity score and also propensity score plus selected variables, or they even adjusted for propensity score plus all covariate. And I think this is too much, but they wanted to make sure their results are not confounded. So typically, and we can use propensity score adjustment without matching. Okay, you can just use it with the original data set. And next one is the inverse propensity score weighting, and sometimes we call this IPW method. And what IPW method is, instead of using we are introduced matching, stratification, or adjustment, what they do is they use technique called weighting, and that will correct differential distributions in patient severity between treatment groups. So weight we used is 1 over propensity score for users. And for non-users, weight is 1 over 1 minus propensity score. So what does this mean? This means weighting is the inverse of the probability of the given exposure. So for users, given exposure is exposure, aspirin. For non-users, given exposure is non-aspirin. So you compute 1 over probability of not using aspirin. So that is 1 minus propensity score. The final analysis, and you conduct Cox regression, mortality is outcome, aspirin is exposure variable, okay? And we don't adjust for propensity score. Instead, we weight this Cox regression by inverse of propensity score. So let me explain how the weighting works. So this is a graph, and I plotted each patient propensity score for users and non-users. So red is users and blue is non-users. So you can see higher the propensity score, you have more patients with higher propensity score with aspirin groups, and you have more patients with smaller propensity score with non-aspirin group. And this imbalance causes bias, okay? Because they are sicker users are seeker to begin with. So we need to correct this sampling bias. Okay? So that's where weighting becomes useful. So for this person, aspirin user, and whose propensity score is 0.8, and the weight would be 1 over 0.8, so that is 1.25. And for this person who is non-user, and propensity score is 0.75, okay? And this person is non-user, so you compute weight as 1 over 1 minus 0.75, which is 4. And this person is users, and whose propensity score is 0.25, okay? And therefore the weight is computed as 1 over 0.25, which is 4. And this person is non-user, whose propensity score is 0.2. So weight is computed as 1 over 1 minus 0.2, which is 1.25. Okay? So as you see, higher the propensity score for aspirin users, you have less weight than lower propensity score among users. And lower the propensity score among non-users, weights are lower than the higher propensity score among non-users. What weighting does is you inflate number of observations multiplied by the weight. So you consider this one dot as having 4 dots. You consider this dot having 1.25 dots. And you consider this one dot having 4 dots. And this one dot become 1.25 dots. So let's see what happens. Okay, I'm going to inflate number of observation as weights suggest. Right, that means we are going to weight these gray areas with higher weight. Okay. So by doing this, now we have similar distribution with propensity score, which is more likely patient severity between two groups. So therefore, patient severity score, propensity score is now similar. So the bias is eliminated. You can directly compare outcome of mortality between aspirin users and non-users. So therefore, in the final analysis, you don't have to adjust for propensity score. You just weight final analysis by inverse of propensity score. As we see, doing propensity score is very easy for binary exposure variable. And all you have to do is a logistic regression, okay, where outcome is use of drug and you put the potential confounding factors as independent variable. And then retrieve predicted probability. As long as you know how to do that. And after that, you either stratify and you either do matching or you include the propensity score as covariate in the regression. And the weighting is also easy. Most software does have option of weighting. But one thing I want you to remember in mind, propensity score is easy to do, although it is very important to validate propensity score. And you need to make sure if the propensity score is really providing balance. For example, the data with this example, okay? So table 1 showed the baseline balance between two groups in the original cohort. And table 3 indicate baseline difference after you applied propensity score through matching. And then let's make sure p-value is improved. Okay, so these p-values show unbalance. And let's make sure all p-values are improved. So if you see some p-values which is not balanced, and you need to go back to your logistic regression, creating propensity score, and think about interaction or think about nonlinear term. So you need to tweak propensity score model. Then you check this balance again until you see balance in all variables. Some people include the variable which does not reach the balance as additional covariate in outcome regression. So that's another strategy. And this is a typical plots we use to validate propensity score. So instead of plotting p-value from previous two tables, we are plotting t-statistics. So t-statistics is actually linked with p-value. And higher t-statistics and p-value is smaller. Okay? And so before propensity score matching, you have higher t-statistics. And each of these dots indicate each covariate. For example, the age. Okay? So p-value for age was much smaller. That indicate higher statistics before propensity score matching. But then after matching, p-value become larger. That means the statistics become smaller. So you expect, if you have a good balance and you have all data points cluster around 0. So here they say only one variable, and which actually clearly got worse after the matching. So they may include this variable as separate covariate in the final Cox regression, or keep tweaking propensity score model. Some people ask me whether they can use propensity score for ordinal exposure. For example, they have low, moderate, high dose of drug instead of user and non-user. And yes, you can. Binary exposure variable, we use binary logistic regression. Ordinal exposure, we can use ordinal logistic regression. When you record exact dose of drug and you have continuous exposure, you can easily use linear regression or ordinal logistic regression. And when you have a nominal exposure, for example, you recorded type of drugs, okay, and then there is no order in the type of drugs, and you can use multinomial logistic regression to create propensity score. Here is a technical note in modeling propensity score. When you compute propensity score, selection of covariates must be based on clinical knowledge. Okay, so you don't do bivariate selection or stepwise selection. Never. Second, propensity score model should be more inclusive than exclusive. So you need to include all possible confounding factors. Okay, what is confounding factors? Variable which are causally related to the outcome and which happen to have association with exposure. So when you don't have room to include all of them, it is more fatal not to include the variable which is causally related to the outcome than the factor associated with exposure. So, in for propensity score model, overfitting is less problematic because we use only predicted probability. We don't really look at each beta coefficient. And if possible, it's better to include nonlinear terms or interaction terms to improve balance. Final slide. Summary of propensity score. Advantage. Propensity score can control for effective confounding very effectively. And you actually reduce dimension of many covariates, potential confounder, into one variable. And enable to use observational data to assess causality, which often reflect reality better than RCT. So RCT is more of experimental setting. So, and there are many weaknesses in RCT. So if you want to assess what really happening in real life setting, and it is not bad idea to use observational data. And limitation, big limitation with propensity score, and it cannot control for unobserved confounding. So therefore, even when you have a perfectly well done propensity score analysis, RCT still have advantage because randomization can control for unobserved confounding as well as observed confounding.